How about now? That should do it.
Okay, yeah, we're good.
Okay, sorry, online folks. Okay, and I have to say, this is a rare luxury to be able to give a talk for an hour and a half. I hope I don't bore you, but I started with a talk that was meant to be half an hour, and I kept adding slides to it. I don't think I've quite made an hour and a half long talk as yet, but yes, exactly. It's seeing what happened yesterday. I might not actually get through this current talk in any case. Okay, let me jump right into it. So you can see from the title that something very strange goes on in this material, apart from the cool superconducting properties. What we found in this system is a very exotic charge density wave, which responds to magnetic field. And what you'll see is that it responds to magnetic field in a very peculiar way, meaning that if the charge density wave actually dies when you apply field at values close to HC2. So charge density waves are not supposed to actually disappear with magnetic field, and especially not at values close to HC2. So this immediately tells you that the charge density wave in the system is somehow tied to superconductivity. So that's partly what I'm going to talk about today, after sort of an extensive introduction to this material. Okay. Okay, the people who did the work primarily are Uraniumbased, who's a graduate student in my lab, and Lin Zhao, a former postdoc, with the help of these other graduate students. We had a bunch of theory help from Boston College, ETH, and also UIUC. The initial single crystals that we studied were grown by Sheng Ran, who was who was the person who actually discovered superconductivity in this material. And the ones we have now are grown by Shanta Asaf. Okay, so why are we interested in uranium-based compounds? Primarily because we've known for a very long time that if you want to look for triplet superconductivity, and we're interested in triplet superconductivity for a variety of reasons, including the fact that if you have the right symmetries and the right Fermi surface, some of them might be topologically non-trivial. So if you're interested in triplet superconductivity, one of the best places to look is in the vicinity of ferromagnetic fluctuations. And uranium-based compounds, as you know very well, many of them have ferromagnetism, and many of them have shown to become to be superconducting under pressure or at very low temperatures. And UTE2 also belongs to this class of materials. And actually, the nice thing about UTE2 is that it has no static ferromagnetism, and it has a whole bunch of magnetic fluctuations. So sort of a very nice candidate for triplet superconducting. UTE2 is a very well-known material. It was synthesized in powder form in the 1960s, and it was studied initially because in the 1990s, when the first single crystals were made, people realized that it's a really nice heavy fermion metal. So
Higher volume.
Higher than this.
Yeah. Well,
what do I do?
Online, maybe.
How do I do that?
You increase the volume on your speaker or
There is no way to increase the volume.
You just move the laptop.
Ah, yes, that's true. I could do that.
as far as it
This is an adventure. Okay.
Can I take advantage of break? In your previous slide, when you move from uranium to uranium to uranium two, which product do you have to control?
Say that again, please.
When you move from uranium to uranium to uranium two, which product do you actually control?
I don't know, but I'm trying now sitting here trying to guess. The difference between uranium germanium 2 and uranium 10, what could it be? Sometimes it's just the distance between the atoms. So it could just be that. I'm not sure.
Fermi surface is very nested
And
in uranium titanium.
but I mean, why does that kill magnetism? He's asking about magnetism. He's wondering why these materials are magnetic and this one's not. Sorry, I don't have a single answer. Okay, so yes.
Why was superconductivity only discovered so recently?
Really good question. There is a story. The story is that, there are these fridges that people use. And there are fridges that go down to 300 millikelvin. There are fridges that go down to dilution. There are dilution fridges that go to very low temperatures. There are 1.1 Kelvin fridges, and then there are 4 Kelvin fridges. Nobody went down to low enough temperatures to measure resistance. That's it. I don't think it was anything more than that. They stopped at 1.5 or maybe 1.6 or even 4, and they didn't see superconductivity.
That's not true. Diaoki goes down to very low temperatures. It's the sample.
Oh, he had poor
The
samples.
samples improve, the chemical vapor methods improve.
Well, the thing is, I heard a talk actually, and apparently it's not at all clear what exactly changed in the way they were making samples earlier and they're making samples now.
Yeah.
The CDT samples are not particularly, clean in the sense of triple R's, whereas the flux, molten flux samples are much clearer.
Era samples were better than the previous Aoki era samples.
I think there's something more subtle than that.
Okay, right.
It's got to do with whether or not you have uranium, excess uranium, uranium vacancies, excess tellurium, tellurium vacancies. It's a specific kind of impurity. So that might be true.
But anyway, it wasn't the fridge temperature.
It wasn't the fridge temperature. Okay. Their samples were not similar.
I was always wondered that she learned in Cambridge and just looking Grenoble studying a lot of uranium compound, even the pressure. I just think it's believe why they didn't actually touch it.
It pierces right, and they made these samples and they were okay for all purposes, except they were not superconducting. I don't think they would have thought to themselves, oh, if only we increase the amount of uranium we use. I think they may not have imagined. Yes.
There's some intuitive explanation for why ferromagnetic fluctuations are like racing down towards the.
Why don't we ask the theorists? Yes.
Sure. So they're both orders that involve the two spins being counted. Ferromagnetism is part of the whole pairing of the spins. Triple superconductivity is part of the whole pairing. Yeah, but that's at the ferromagnetic principle point where it's like very big of a manipulation, right? He's winning, but it's not for straight. Okay, it's still the case that slow fluctuations are happening in the parallel spin channel. Okay. It's just that they have quite long. And it's actually good that they happen because you don't want the magnetic sector that would if you want to. Okay, right. So why
do you need to keep this guy under control?
I think you two should have a separate conversation later. Let me just say one thing though. There is a recent work that suggests that you could even have triplet pairing from antiferromagnetic fluctuations. So it's not just that ferromagnetic fluctuations are the only route, but the reason I put the previous slide up is to say that initially, at least decades ago, people thought that that was one route to get to triplet superconductor. Okay, good. So the initial samples were grown by this method called chemical vapor transport. And this is sort of a schematic of the method. This is what the single crystals look like. They're beautiful, big and beautiful. And this is the crystal structure. It's a body-centered orthorhombic IMMM space group. The the way it looks complicated, but it's not that bad. These green atoms and these blue atoms are tellurium, and these red atoms are uranium. So the one way to actually visualize this structure is to think of these trigonal prisms of tellurium surrounding two chains of uranium atoms. So it's a very stripy, chainy kind of material. The low energy bands are actually coming from the 6d uranium orbitals and the tellurium 5p orbitals. So both of these orbitals live close to the Fermi energy, but remember, this is a heavy fermion compound. So there's also the F band that eventually comes up close to the Fermi energy at low temperatures. So the point group is, sorry, it's down here, is D2H. And you heard this yesterday, and I'm not going to go into this very much, but if you want an odd parity superconductor, then you can have one of these four irreducible representations, which is AU, B1U, B2U, and B3U, and linear combinations of these. So if you have only one of these in your order parameter, then it cannot be chiral. If you have two of these combined as, A B1U plus I B3U, then you end up with time reversal breaking a superconductor. So
These are all single component.
these are just the irreps, single components. So there's still a debate on what the order parameter actually is, and I'm not going to go into that right now. The normal state, like I said, is the heavy fermion, and you can see that from the resistivity. Resistivity is a metal, but resistivity goes up as temperature goes down. This is because of the increasing spin-spin interactions. And once the Kondo coherence temperature is reached, then resistivity plummets. So this is this is the signature of heavy fermion physics. This is susceptibility, and the A-axis, this is this red curve, is this is the easy axis, and you can see that. Sorry, once in a while this goes. So you can see that there's no magnetic ordering down to the lowest temperatures, so that's that. So it's paramagnet. Okay. So just to remind you, before I show you STM data,
In your previous paper, A-axis activity at shoulder at around what, 20K?
yes, there is a shoulder. They don't know what that is.
Yeah, and tellurium one is not saying anything about this change in tellurium one more than important.
These chains of tellurium 1 and tellurium 2.
Yeah, so you see on this, you show tellurium two that change
No, they're all important. They're all important. The reason this is marked this way is this is the nearest neighbor distance, and therefore this direction is called tellurium chain. But when we cleave in some strange direction, you'll see, and then we call this direction also chains. It's okay. They're all sort of chain-like. Okay. So just to remind you what a heavy fermion system is. So, the simplest way to think of a heavy fermion system is that you have this conduction band, and then you have this very narrow F band, which lies somewhere below the Fermi energy, and it's singly occupied because of Coulomb interactions. And so you have, in fact, it's so narrow, you can even think of these spins as localized spins, right? And then what happens in these materials is that there's an interaction between these localized electrons and these conduction electrons. And like in the single impurity Kondo effect, this interaction strength gets larger and larger as you decrease temperatures. And finally, at very low temperatures, you get into this Kondo a coherence state. In this coherence state, the localized moments are completely screened. At least if you have a full Kondo effect, you have full screening of the localized moments. The resistivity plummets because you don't have any spin-spin interactions. And because of the strong interaction between EC and EF, meaning this interaction mu this becomes larger and larger, two things happen. One is that original F band moves closer and closer to the Fermi energy. And the other is that because of the hybridization, you open up a gap. So in the end, you end up with this gap at the Fermi energy, right? And depending upon whether your Fermi energy is in the middle of this gap, in which case it's an insulator, or it intersects one of the bands, you have a metal. And in the case of uranium ditelluride, the Fermi energy intersects the conduction band, and you have a metal. So it's actually a heavy fermion metal. However, with this extremely large density of states sitting right next to the Fermi energy, which is important to note. So now let me show you STM data on UTE2. Here's topography, and here's the crystal structure. Looking at this, you don't realize that this might even cleave. Doesn't look like a material that wants to cleave, but in fact it does. It cleaves along this plane, which is the 011 plane. And we know that because we can look at the heights of the step edges, we can look at the distances between the atoms, and these are the tellurium atoms, right? Oops. Thank you. That's perfect. Is that better? Okay, so that is better. Thank you very much. So these are the tellurium atoms. There are two tellurium chains. This is tellurium 1 and this is tellurium 2. So this is one of the telluriums. This is the other one. And in between is uranium. And in fact, even though this topography is dominated by one of the tellurium atoms, it turns out you can see all three atoms that are close to the close to the surface. This tellurium chain, this uranium chain, and this tellurium chain, we have access to all of that from the topography. Because if you Fourier filter out this one, you can see the other atoms. Okay, so this is what the DI/DV spectrum at high energies looks like. This is pretty high energy scale, 40 millivolts. So you see this funny line shape, and many of you might be familiar with this line shape. This line shape is known as a Fano line shape. And it's a very peculiar line shape, and it arises because of a very interesting phenomenon, which is that when the electrons leave the STM tip, they have a choice. They can either go directly into this very high density of states band, or they can go into the continuum. And there's an interference between these two tunneling paths that leads to this funny line shape. When you see this line shape, what you should imagine in your mind is that there's a sharp resonance at this energy sitting right here. So there's a sharp peak in the density of states here, but the problem is we're not able to access that directly. The tunneling into that sharp state is highly suppressed because that sharp state has F character, and F orbitals don't stick out into real space. And because tunneling into that is suppressed, and there's this interference, you get this Fano line shape that we see in STM data of basically all heavy fermion compounds. Did anybody have a question? Okay. Okay, so yeah, so this is the Fano line shape. The nice thing about knowing what this is you can fit it, and this black curve here is the fit, and from that you can get the width of the resonance and the position of the resonance. But from the width of the resonance and from the width, you can get the quantum coherence temperature. And the quantum coherence temperature from the width is about 30 Kelvin, which is right here, which is exactly where I should have shown you earlier, where the resistivity starts going down. Okay, any questions about this before I proceed? Okay.
Yeah, can I ask a question?
Yes.
Hello, can you hear me?
Yeah.
Hello. Hello. Can you hear me?
I don't know if your song.
I thought I was unmuted.
No, I think you're speaking to the person.
Oh, that.
Or maybe just type your question and I can read it out later.
Sure, yeah, I will type. Yeah.
Yes. There is a lot known. There's, there's spin-orbit coupling, and there's crystal field, and all the level split, and there's a lot known about that. I can point you to some reference. this thing. That's a good question. It could be actually. It could be. I don't think anyone's thought about it in that way. It could be. That's a very good question. You could actually check that. You could do spectroscopy and check it actually. Yeah.
Could that also be the reason why the thesis?
No, so this is definitely condo.
It's definitely called.
Yeah. Because this spins. By the way, I have to say one thing though. In this material, the spins are not fully screened. So below the Kondo coherence, there's still some spins left. And otherwise, where are you getting all these spins from to do all the fluctuations and stuff? So there's still some spins left that are not fully screened. That yes. Well, there's spin fluctuations. So basically, if you really had fully screened spins and you were at very low magnetic fields, Kondo shouldn't get affected by low magnetic fields. You shouldn't see anything. But in this material, it behaves like there are spinful objects at low temperatures. Even from USR, you can see there's spinful objects at low temperatures. So there's got to be partial screening, otherwise when you get these spins. No, so I'm not saying they're ordered.
It's an Ising-like system. That's the reason why. That's Van Vleck magnetism the energy direction.
So there is, I'm not saying they're ordered, they're still paramagnetic, but I don't believe they're fully screened. Okay. So, yeah, let's talk about superconductivity, which is the interesting thing in uranium ditelluride. The first thing I want to show you is, you'll see why I'm showing this in a second. The first thing I want to show you is that if you look at what happens to superconductivity in a magnetic field, you find something really extraordinary. We just, we're so used to this that we say it in two sentences, but it's actually quite extraordinary. The extraordinary thing is, usually when you apply a magnetic field, you kill superconductivity, and that's that. But in this system, you apply a magnetic field, and initially superconductivity does go down. But depending upon the direction in which you apply a magnetic field, you have another superconducting phase. Okay, this is called reentrant superconductivity. So that's the first thing. And the second thing is, and then not in this direction, but in a different direction. Sorry about that. In a different direction, if you apply a magnetic field in this direction, so this angle is from the B to the C axis. This is the B axis. So somewhere in this direction, you kill superconductivity, and then it stays killed. And then at some high magnetic field, you get another superconducting phase. So it's very strange, and typically this kind of phenomenon where you get reentrant superconductivity with magnetic field is seen in triplet superconductors. Okay. So this is why I bring this up. This is the first indication that this actually might be a triplet superconductor.
Can I ask a question?
Yeah.
So the reentrant phase on axis, you're going from superconductivity to superconductivity.
Correct.
So what does that look like experimentally?
So I don't do transport. I'm an STM person. So I don't
transport.
I'll tell you one thing, they don't understand this phase transition at all. There's some indication that, let me see which one. I think this one might be a second order phase transition. They don't understand. They're trying to figure out what's going on.
How is it?
I think this is the heat capacity.
They do say heat capacity.
It might be other percent.
Yeah, so this is a very strange phase type. Sorry? I'll show you another.
The ABC, how is it related to the change direction in the
So A is along the chain direction. A is along the range.
put the field along A, would happen this dies?
It dies. And it's also the easiest. Okay, just because yesterday there were so many questions on this other 2.1 Kelvin sample, I thought I'd show you some data on that sample. So let me just clarify. The initial samples had a TC of 1.6 Kelvin. And then later on, as the samples got cleaner, the TC has gone up to about 2.1 Kelvin. The question you might ask is, are these two superconductors the same? And I'll tell you my view. My view is that in all the ways that matter, these two superconductors are probably the same. I suspect that the differences that people are measuring in transport, penetration, specific heat, whatever differences people are measuring, is simply because one sample is dirtier than the other. That's just my gut feeling, but I can't be 100% sure. Let me just show you some data though. The first thing is, in this high, let's just call this a high TC sample. In this high TC sample, you see the same reentrant superconductivity. This looks complicated, it's not actually. This is nice because you can see along this axis is the transition temperature. This surface is H parallel to A, this surface is H parallel to B. And if you look here, this is the direction where you have the reentrant superconductivity, and that's exactly what happens. So as you increase field, you get this new superconducting region, even in this new sample. Okay, so in that sense, these two samples are quite similar. The TC is not that different. It's between 1.6 and 2.1 Kelvin. Let me show you another thing. HC2 for the 1.6 versus 2.1 Kelvin sample. This is HC2 for the 1.6 Kelvin sample along the three directions. In the direction in B, HC2 basically is extremely high. Okay, this is another indication that this is a triplet superconductor. In the A and B directions, I've drawn dotted lines here to show you that in both of these directions, HC2 has gone up a little. So in the higher TC samples, HC2 goes up, let's say in the A direction from about 5 to about 7.5 Tesla, right? And in the B direction correspondingly, and the C direction, it goes up from about 7.5 to 10, 12 or something. Yes.
Just to be clear, you're talking about the floor broad and actually coming at the beginning of the superconducting state. You're not talking about the fluid state, right?
Here?
Yes.
Yeah. Here, this is the regular
Down there.
down there. Correct. Exactly.
These temperatures check well within this fluid transition or the fluid peaks and specific heat.
So it's a controversial subject. For these samples, there is no split transition.
But if I were to take a sample 2.1, 1 peak and 1 fluid melt, what are the second peak?
Here in the 1.6 Kelvin samples, it's very close to 1.6, just about less than a Kelvin.
It's not two different phases. It's basically Sunday Kelvin will not 6 Kelvin sample.
The 1.6 Kelvin, some of the 1.6 Kelvin samples showed 2 peaks, but they were very close to 1.6 Kelvin. Yeah, they were not close to 2.1. Yes.
I agree with the statement that it's most likely a triplet because you see that the HC2 was off the content, it makes case on the conductor compared to the But what about the orbital? The fact that HC2 is infinitely new, that there is not even orbital. So how do you relate the p direction with the direction of the dimensional thermostat?
I think the p direction is complicated because of this. So something else is going on at higher magnitude.
So there should be some change on the thermostat. This is a constant.
They're at higher magnitude, about 15 or 20 Tesla. Yes. Yeah. Okay, so let me now finally, with all this background, I can show you the night shift, which I was saving for the last. Because that's what one goes to immediately to say, oh, it's a triplet superconductor. You know, why do I care that it's such a triplet? That's what makes it interesting. So I think it's a triplet superconductor. However, let me just show you this. Initially, when they did night shift measurements, they found very little change across TC, and everybody said, yay, we found a triplet superconductor, okay? And that's this gray, all this gray data is actually no change across TC. And these two, all of these gray data points were actually done later on. The first samples, they saw no change across TC. Then they did some more measurements, and then they found this gray data where in the A direction, there's no change across TC. But in the B, there's a tiny B and C, there's a very small change, nothing like what you would expect for a singlet, okay? And the more, this data that I'm showing you here in red and blue and green, this is actually on the high TC samples. And there you see that there's a pretty large night shift in the A direction. But again, the B and C directions, the night shift is very small compared to what you would expect for a singlet superconductor. So what this is telling you is there are a couple of things. One is this is not inconsistent with this being a triplet superconductor. However, this suggests that whatever the D vector is, it's a three-dimensional D vector with components in all of these three directions. Okay, so that's all.
Sorry. Quick question. Can I just check the scale? So delta K in percentage means that full singlet will go down to -100.
I think so, yeah.
It really is.
Yeah, it's pretty small.
I think
Yeah.
delta K percent is the night shift in percent, right? And the answer to your question is that it's very difficult to set the actual scale, convert the night shift, convert the night shift to an actual susceptibility, right? So in fact, that is the Achilles heel of all of these things. And in fact, one of the things that on the roof and that's the other thing.
Oh, yeah, are you saying that you don't know if this doesn't mean that singlet would be 100%?
That is the night shift, as in a percentage shift.
I thought they divided it by the normal state. This one is divided by the normal state. Like,
Okay.
does that help?
Possibly.
Yes.
Possibly not.
Oh.
Because
Okay.
Because the thing that changes the speed susceptibility.
Okay.
But it can have other contributions. So to convert it into a susceptibility, it's not simple.
Yeah, and even if you divide it by the normal state, it doesn't quite.
Surely the night shift 100% means relative to an isolated nucleus.
Yeah.
Right?
So not in a solid.
Yeah.
Okay, I think maybe the best thing to do, one thing you could do is, I don't know if that makes any sense, but compare it with a D-wave superconductor, for example, and look at the actual night shift done this way, divided by the normal state shift. Yeah. Yes.
Can I just make one here? So these data figure for two PET samples, one for gray and one for color.
Mhm.
And is it correct that two samples show different behavior?
Yes.
Right. You kind of imply that all seem to be consistent, but to my eyes, in particular along the x-axis, the samples completely different.
They're trying, yes, so these two directions are the same. This direction is puzzling. However, A is the easy axis. The 1.6 Kelvin samples have impurities. And there's that people are trying to figure out how one could explain this on that basis.
The resistance ratio is like 30 times better. It's like 1,000
correct.
versus 30 in the colored one.
That's
The
correct.
residual linear specific heat is tiny compared to
Correct.
those old.
In the old one, the residual specific heat was half of the normal value. And here it's almost zero. So I don't know if there must be a way to explain this based on that, but I'm just saying that.
But I guess that this night should basically measure the skin set we have at the visual energy line. And so for impurity will certainly because that was probably, but I think what transport is one thing, but this actually thermodynamic quantity.
Yeah, well, I have nothing useful to say about this. Okay. Yeah, so another thing is that, the initial, 1.6 Kelvin samples, there was, penetration depth showed this kind of behavior, T-square behavior, which indicated that there might be point nodes. And now there's the 2.1 Kelvin sample. This is very new data, and therefore I would urge everyone to wait and not jump into conclusions. But at least this data shows that actually there are no point nodes and that it's fully gapped. So it's a fully gapped superconductor, which actually is, if you look at all the possible autoparameters, there is one that would be consistent with actually a topological superconductor. We haven't discovered any of these. It would be pretty nice. I would be happy if this didn't have, this were a true 3D topological superconductor. It might even explain what we see on the surface. But like I said, this is just one experiment, and we should be sort of careful jumping into conclusions. Yes. So they have this. This is the data. This is this blue. The two blue curves are their new data, and the fact that it goes to 0 is how you see that it's fully gapped. It says thermal conductivity in 0 temperature is vanishingly small for both magnets.
You've been there before, right? So what should be the power exponential of the one?
They have fitted, and they believe that it's vanishingly small. And they did look at the behavior in magnetic field, and everything is consistent with having but like I said, it's just one experiment, and we need to do more. For example, we need to do penetration depth. Okay. Let's now look at the superconducting gap with STM, finally coming to STM data. So this is what, this is the topography again. You can see the tellurium stripes. Uranium, this is the A-axis in this direction. If you take a line cut in this direction, no STM person would ever publish. Wow, I'm loud right now. Just when I started talking about it, no STM person would happily publish this. We did. That's because that's what the sample looks like. What happened?
Exponential dependence.
This is
Yeah, this.
okay. Yeah, that's better. So, so here you see a small dip. I'm calling it the superconducting gap. You should not believe me. And the reason you shouldn't believe me is, let me actually skip over here. Look at this. So this is the dip that we see in uranium ditelluride. This is another superconductor with a very similar TC, which is not going to 0 density of states, but it's pretty low, and you see nice coherence peaks. And this is what we saw with we picked up a uranium flake on the tip, and you see the gap doubling. But it still doesn't go to 0. And so this is a very strange, shallow gap-like feature. The only thing I can say is it disappears, at least it gets suppressed, highly suppressed with magnetic field. In this direction that I'm, HC2 is like 12 Tesla or something. At 300 millikelvin. Okay, now I can show you this. So here's a sample. We did Laue to make sure it's in one phase. We looked at the specific heat of this particular sample, and then we did the temperature dependence of this gap-like feature, and it disappears close to the TC. So everything, magnetic field dependence and temperature dependence, are all consistent with this being the superconducting gap. We actually have better data now where the gap is slightly better, but really this large residual density of states continues to persist. And the question you have to ask is, what is this density? Why do you have so many quasiparticles inside a really nice superconductor? And the lovely answer would be, it's a topological superconductor, and these are surface states. right? Like that would be the best possible answer. Shuchi's experiments yesterday's, there's some indication that that might be true, but we still have a lot of work to do. Okay. So let me show you some very interesting data that we don't understand on the step edges of the sample. So if you look at the step edge, and now I'm beginning to slowly run out of time. I have to hurry. Okay. If you look at the step edge, then far from the step edge, number 20 would be this one, number 1 would be this one. So let's start here. This is far from the step edge. You see this wider superconducting gap. And then you get close to the step edge, and then you see some very strange feature right at the step edge, which looks like this. So it's got this funny line shape. Look at this energy scale. The gap itself, I have to tell you, is 250 microvolts. It's tiny, okay? So, and this funny thing lies inside the gap. So the peak is somewhere 150 to 200 microvolts. That's the, and then correspondingly on the other side of the Fermi energy, 0 is the Fermi energy, you have a dip. So it's not nothing. On the other side of the Fermi energy, instead of a peak, you have a dip in the density of states at the same energy. Also, if you go to, so this is like, the way you think about this is a terrace. So there's a step up on this side and then a step down on this side. If you go to, let's say, step down, then you see the peak above the Fermi energy. You go to the step up on this side, you see the peak below the Fermi energy. So basically, the position of the peak with respect to the Fermi energy is sensitive to the direction of the normal to the step edge. Okay. And then it's the same thing. So this is the a-axis, by the way. If you go to this is the trench, the same thing. So the direction of the normal to this step edge is to the right, and therefore you have a peak above the Fermi energy. The direction of the normal on this step edge is to the left, so you have a peak below the Fermi edge. Now there's a lot of problems with this. Before I should tell you the problems. Here's the superconducting gap, and here are the two spectra on the two step edges. And let me just tell you, even if I separated, so the coherence length is nanometers, even if I separated these by hundreds of nanometers, you would still see the same thing. So this happens way on length scales, way above the coherence length. So a couple of things here. Here's the superconducting gap in dotted line. These two peaks on either side are exactly symmetric. Okay, so if you look at these two peaks together, you have particle hole symmetry. The dips are also exactly symmetric. Okay, so all that is great. And so these things have a handedness, meaning that this peak is sensitive to which direction you are facing on the surface. Okay, so there's a chirality here. I didn't mean to do that.
Yeah, before going that the interpretation, the simple statement between that state of your bound state, local state, on either side, you're one above fermion one below, right?
Yes.
And then you do that kind of science of that.
Only in the geometric sense of chirality, right? And to say this has something to do with actual chiral states, you have to take a couple of steps. And we're not even sure of how to understand this.
You know what this local state is?
No, so there are many questions. First, whenever you have a boundary or in it, sorry?
If that's what it is. He said, do you know what this localized?
Yeah, if it is a localized. At any boundary, you have Andreev bound states. So anyway, the Andreev process happens, and that could give you a bound state. We don't know exactly what this is. It does span the superconducting gap on either one side or the other side of the superconducting gap. So it could be a propagating state that lives on the edge. We don't know. So, okay. So then, this is just quickly to show you, because I have to show you the charge density wave. Yes?
There's this step because there is, so how do I understand the step? There is the uranium dichloride on both sides, but there is
A unit cell.
Okay, so it's one more layer above.
Correct.
Okay.
So if this disappears, this feature disappears at TC. It disappears with magnetic field, exactly where superconductivity is highly suppressed. So it's got all the hallmarks of being associated with superconductivity. Okay, because I don't have time, I'm going to go through it quickly. So then we also found 45-degree step edges, and there you see a beautiful particle hole symmetric feature right at zero energy, right? And you can call this an unrefined state if you like, but then these, I don't know what to say. Okay, one last thing before I move on to the charge density wave, which is, this is really interesting. If you ask what does the IV look like, it looks very interesting. So this is an IV on the edge, and what you should see, these are IVs on the two step edges. So if I just subtract a background straight line, right, then what it looks like is this. So on one step edge, the IV looks like this, and the other it looks like this. So that what this is telling you is that depending on the step edge, no matter what your bias voltage is, you either have excess current or less current. And this funny feature, IV in the IV, is exactly what gives you the signal, which is, this is the derivative of the IV. So you see these two peaks have to do with this funny gap-like feature in the IV now. And this is our lock-in signal exactly at the same position. So what I'm trying to tell you is that in many, many ways, this line shape is extremely funny. And one of the funniest things about this line shape is, of course, there's no particle hole symmetry at any given point. If you want to restore particle hole symmetry, you say, okay, look in the vicinity of the coherence length and integrate the density of states. But even if we did that, we would not restore particle hole symmetry. So the only way to restore particle hole symmetry is to include that thing that lives 100 miles away, okay? Which is very, very strange. Okay, so I'm not going to go much further. We don't understand this. There's one hand-waving explanation we had, which included the existence of these chiral states living on the surface of this material. But in the interest of time, let me just go to the next thing, which is, and this is the thing that I'd like you to think about if you have any time. Okay.
This is important for this. This is exactly the thing that nobody understands.
Yes.
Right? Which is how you made the logical jump from these line shapes to same as the current.
There is a step missing here. First, in order to get this line shape, the only way we could think of getting this line shape. So if you have, let's say, these kinds of linearly dispersing states living on your surface, and you break inversion symmetry, then you would get particle hole symmetric features. You would either see this thing or this thing on the step edges, which would, you would see things above and below the Fermi energy. You would see a flat density of states. The only way we could think of explaining this is to imagine that there is a chiral state living on this sample. And then when you go to the edge, for the way you tunnel into the edge, you preferentially tunnel into one momentum or the other. And then that way you would pick up all of these states and not these on one step edge, and you would pick up all of these and not these on the other step edge. And but that would not happen if you had helical states. That could only happen if you had chiral states.
Kind of Doppler shift.
It was much simpler than that. The idea is that as you have an SDM tip, you're at the step edge. The electrons, although there's no conservation of momentum, the electrons that are going in, they come in, with some preferential momentum, and that preferentially selects these or these. That was our I'm not sure. That's a very hand-waving explanation, but I could not think of any other way except this to get this kind of line shape.
Correct, you used a similar argument with your samarium chloride tips.
No,
Similar argument.
not exactly. We can talk about that later. Yes?
Wouldn't that imply that the results should be somewhat different? Or is the method by which we preferentially tunnel?
No, that's got nothing to do with it. That's got to do with the way tunneling happens.
on what aspect would give them momentum balance?
Because if you have, you can just think about it geometrically. If you have electrons just spewing off the tip, then you can imagine that certain electrons going in certain directions would not hit the edge. And normally you don't see this because at anywhere you go, you don't usually see chiral edge state. You have, if you have electrons at positive K, you also have electrons at negative. But this is a very rare situation where you actually have chiral states. So maybe we're seeing something that hasn't been seen before in tunneling, in terms of momentum selectivity. Very hand waving. I'm not comfortable. Yes.
Just to make sure, these two step edges are related by a mirror plane.
Yes.
Is that mirror plane the symmetry of the bulk crystal?
It's a symmetry of the bulk. On this surface, actually, the two directions are different, in the sense that if you look at the way the telluriums are laid out, the bulk has mirror symmetry, but on this surface, it's not. No, but we did check that it's termination independent. So even though on each step edge, you can have two terminations, tellurium 1 and tellurium 2 terminations, it makes no difference to this line shape. Yes?
But then for the 45-degree step edge, is there mirror symmetry?
I don't think so. No, I'm not sure. I'll have to look at the crystal structure carefully. I can't do this quickly in my head.
What's the mirror we're talking about? Like the middle of the or along?
Along.
And what's wrong with that with the middle of that? You're selecting.
Well, that has, there is a mirror in that. Yes? Yes, and I will, this we see even in the 2 Kelvin cells. Okay, all right, now.
Online post up. This is from CD Ghosh. Are the chiral edge states spin polarized? If yes, are there spin polarized STM data for these step edges?
We haven't done spin polarized STM yet. It's complicated. For spin polarized STM, you need some contrast mechanism, and we would have to, I guess, figure out what that contrast mechanism would be, but we haven't done it yet. Okay, so now the question is, what else do we see? And let me show you something really interesting, and that is this charge density wave that I was talking about. So here's the surface again. I show you this because I want to show you the 3D Brillouin zone. Here's the 3D Brillouin zone. The surface that I'm looking at is this one. This is the Brillouin zone for that surface, okay? So just remember the shape. There'll be a question at the end. Okay, so now if you take this topography and do a Fourier transform, these are the tellurium peaks, Bragg peaks in the Fourier transform. 1, 2, 3, 4, 5, 6. The way to think about the surface is like it's a squished hexagon. That's the best way to think about the surface. So it's squished in this direction. And then in addition to these Bragg peaks, we see these 3 extra peaks. And the question is, what are these 3 extra peaks? And so, by the way, this is the Brillouin zone that I was talking about, superimposed. So these 3 extra peaks live on the boundaries of the Brillouin zone. Coincidence? I don't know. Okay. So are these indications of a charge density wave? If you look at DIDV maps, so this is the topography, this is the DIDV map at 1 energy. Actually, this is dominated by this peak here. This is the Fourier transform of this DIDV map. You can see these stripy features that you couldn't see the topography. And then at the Fermi energy, you see these close to the Fermi energy. You see these that's dominated by these 2. You see almost every second tellurium atom is bright. It's not perfect. And the reason it's not perfect is it's not that the order, it's not disordered. The CDW is really nicely ordered. It's because these 3 CDW peaks are incommensurate. And so you see them nicely only when they actually lie commensurately on the lattice. Whenever they're off the lattice, you don't see them very well. So there are these three incommensurate peaks, and the question is this quasi-particle interference or is this a charge density wave? And to answer that question, you can look at the energy dependence, and so this is energy. This is a line cut in these three directions. So this peak is represented by this dark line. So you can see as you change energy, this is momentum. So the momentum of this peak doesn't change as you change energy. So all three peaks, the momenta don't change. So this is a charge density wave. And this is what the charge density wave Q is. And it's even though this is 0.5, it's not commensurate because it's in the wrong direction. Yes.
Just to remember the premise of the charge dimension,
Yes.
all those interactions relate.
The one problem with that is that Fermi surface was for a different surface. This is a different surface entirely, and so you would have to project that Fermi surface onto this surface.
So that's
It's just we don't know enough about the Fermi surface. There's very little artist. We're slowly beginning to learn more.
it could not be that for these three different directions.
No, so these three CDWs, I'm calling them 1 and 3, but they're related by symmetry. Is that what you're saying? So these two are related by mirror symmetry. And this one is actually related by addition of Bragg vectors. So they're all connected to each other. But you'll see they actually do behave independently. Is that what you were asking? Okay, we can talk later. Yeah. Okay. Yes. We couldn't really find that. We haven't been able to. If you guys have, then you should check. Okay, so this is just quickly, this is neutron scattering data. They see some the neutron resonances. I just want to show you where the position of those resonances are. So this is our Brillouin zone. These are our three CDW peaks. And the neutron resonances are here. So our peaks have nothing to do with the neutron resonance. Okay, for whatever that is worth. Okay, so here's the interesting thing. If you turn on a magnetic field, which you should not expect to see anything happening, usually for a charge density wave. But here's a 3D view of the 0 Tesla. These are the three peaks. This is one. Oh, you see one. This is pretty tall. 2, 3. In a magnetic field, the first thing is, let me just tell you, this is a perpendicular magnetic field to this plane. So in this direction, by the way, HC2 is about 12 Tesla or so. So at 10 Tesla, which is below HC2, what we see is all three peaks get suppressed. So all of the three CDW peaks, you don't see, oh, here it is, 1, 2, 3. All of them are getting highly suppressed with field. This one is almost gone. So first, magnetic field breaks this mirror symmetry, which makes sense actually. But the important thing here is that these peaks are getting highly suppressed. So you can see it in the line cut as well. So in this direction, you can hardly see this peak anymore. These two peaks have gotten pretty suppressed. Okay, now we know, yes. Yes, and I can show it to you later. I don't have it right. Yes. So sorry. So you know that the sample is extremely sensitive to magnetic field. A few degrees off, we're at 24 degrees. A few degrees off from 24, HC2 changes a lot. So this was just fortuitous. We happened to cleave the sample such that the sample was at 11 degrees away from our previous sample. And now you see that at this angle, at this 11-degree angle, actually HC2 is much smaller. It's around 10 Tesla. And now, not only do the three peaks get suppressed, this is 0 Tesla, 5 Tesla, and 10 Tesla. At 10 Tesla, all of these three peaks are gone. So this is 0 Tesla, you see the peak, 10 Tesla is gone. So this is this peak. Same here. This is 10 Tesla. right? This is within the noise, mostly gone. This is gone. All three peaks are almost gone at 10 Tesla. So the question is, why is this happening? Why would a charge density wave get suppressed at HC2 or close to HC2? So one possibility, this was proposed by my colleagues Eduardo Fradkin and his student Julian Meyman, is that there is a pair density wave in the system, right? So let's say you take a Ginsburg-Landau theory of a uniform triplet order and a triplet pair density wave order. It doesn't have to be triplet, by the way. The only reason we thought about a triplet PDW is because it's sensitive to magnetic field direction. So this, we have to explain the sensitivity to direction somehow, and one way to do that is to assume a triplet PDW. Then you can have a charge density wave order as a daughter order. This CDW will have the same wavelength as your pair density wave, and of course double it as well. And this PDW state explains the direction sensitive behaviors of the CDW in magnetic field. Okay, so this is a hand-waving explanation. Supposing you had a PDW, and the PDW also sort of, to get the CDW, you need two ingredients. You need a homogeneous superconductor, and you need a pair density wave. The combination of these two things gives you the charge density wave. If you kill homogeneous superconductivity, you will also kill the CDW in this scenario. Or if you kill the pair density wave, then you will, you might kill the charge density. So that is the scenario. In this case, of course, we know the homogeneous superconductivity is getting destroyed by magnetic field, and that is how the CDWs get destroyed by field. Yes?
Sorry, forgive me if I'm misremembering, but didn't we see yesterday that the CDW survived temperatures above the superconductor?
Yes, and so that's our data, and I'll tell you where it goes away. We've actually, so our first time we did it, we went to 1.6, 4, and 10. We saw it gone at 10. We saw it was there at 4. But just like Shuji, we did experiments last month, and we know now it goes away. You can't believe this at 4.8 Kelvin.
How could it be a daughter that survives in the absence of superconductivity?
Yeah, so I have asked Eduardo and Julian this question, and they assure me that there are scenarios where you can have a charge density wave state that persists to a few degrees above TC, even if it is a daughter order of a PDW.
They explain to you how that is possible.
So one simple way would be if the PDW were to persist, even though the homogeneous component is destroyed. So that's one simple way.
That would, but then the PDW would be superconducting also.
Would be superconducting, and then if this is happening on the surface, you might not see it in transport measurements. What do we see on the edge? I don't have an answer to that. I mean, it should be there. I mean, why not? Yeah. Let me keep going, and then when I stop, you can ask me again. Please ask me again. Okay.
No, well, we need to stop before the end things, do that. The end
Okay.
is in 20 minutes, 15
Oh,
minutes.
that's plenty.
Okay.
You see any gaps as this?
We haven't done a careful, we haven't done, gap. No, we haven't done any careful studies of the gap as a function of temperature. We have a problem with doing careful studies. Sorry. Yes.
Is the impact of this your only parallel colors?
Nothing as far as I know. The CDW is weak. It's weak. You can hardly see it in the topography, although you see it. It's weak peaks in the topography. I don't know. It's probably gapping off small portions of the Fermi surface. It's got the symmetry of the lattice. It keeps the symmetry of the lattice. So I don't know if it's okay, so the interesting thing here is, let's say we believe this just for 1 second, okay? Just for one. Let's say we believe this, that there is actually a PW. Is there a testable consequence? Okay, so one testable consequence is the following. So according to the Ginsburg-Landau theory, if you turn on the way the CDW disappears should be the following. When you turn on a magnetic field, you get vortices of both the homogeneous component as well as the pair density wave. And what Eduardo and Julian were able to show is that if you have isolated vortices of the pair density wave, then at those locations, the charge density wave should develop a dislocation, where the phase of the charge density wave should wind in real space by 2 pi. So in fact, these vortices should be associated with pairs of absolutely winding dislocations. And in theory, at the center of these dislocations, the amplitude of the charge density wave goes to 0. And therefore, as you increase the magnetic field, you increase the number of vortices and you increase the number of these dislocations with opposite binding. And that's what kills the charge density wave. That's what theory would predict. So let's see if we find these dislocations, okay? So can we see these dislocations? Do they have anything to do with the disappearance of the charge density wave? All right, so fortunately, in STM, when you do a Fourier transform, you have access to the amplitude of the order parameter, the charge density wave, but you also have access to the phase of the charge density wave. So you can extract that from the Fourier transform quite easily. So let me actually show you what that data would look like. So here's for some region of topography, which I don't show here. This is the Fourier transform. Here's the extracted amplitude. Here's the cosine, this term, the phase, right? Total phase. And here, what I'm plotting is just this relative phase. What this relative phase captures is if you have a phase shift in the charge density wave at some given location, then you would have an extra relative phase that would be position dependent. Okay, does this make sense to everyone? If the charge density wave were homogeneous everywhere in space with no phase shifts, then this relative phase would be 0. All you would have is a cosine term, that's it. So this relative phase actually captures any phase shifts in the charge density wave, and a phase shift is a dislocation, okay? So you can see already for this topography, you have a pair of dislocations here. Now, let's talk about the phase of these dislocations. Because we can measure the phase, we can plot it as a function of angle as we wind around one of these dislocations. So here we're winding around this dislocation, and you can see that the phase winds by 2 pi as we go around. Now let's pick another one. Sorry, this is cut one. So this is this one, and this is the other one. Now, if you pick this one, it goes in the opposite direction. So I've shown you 2 things. One, you have these dislocations in the CDW. And the second is you can have dislocations with opposite phase winding. And just to, as a comparison, if you go somewhere else where there's no dislocation, the phase just doesn't change as a function of that. Okay. And now let's ask what happens as you increase field. So this is 0 Tesla, 5 Tesla, 9 Tesla, 10.5 Tesla for the sample where the CDW disappears with magnetic field. What we find is that you can see that you have an increase in the number of dislocations. And not only that, the dislocations come in pairs. So the color here represents the winding that I just showed you. So you can see pairs of dislocations with opposite winding emerge as you increase magnetic field. Okay. So this is really cool. The question you must ask is, what is the proof that it's these dislocations that are actually killing the charge density wave? And we can actually check that. So we know that the amplitude dies over, as a function of magnetic field, but now we can plot the amplitude in real space as a function of location. So here is a plot of the amplitude as a function of location. These are amplitude maps. These are the relative phase maps. And you can see that the amplitude is suppressed, But we can do more than that. What we can do is we can take this amplitude map and we can ask, where is the amplitude suppressed? Okay, so is the amplitude suppression correlated with the positions of these dislocations? So right here below, these dots represent all the dislocations in this field of view. This is, I think, at 9 Tesla. This is the amplitude map. These areas represent areas in the amplitude map where the amplitude goes to 0. Okay, and you can see that there's a direct one-to-one correspondence between the regions where the amplitude goes to 0 and the positions of the dislocation. Okay, so the CDW disappears because of the creation of these pairs of dislocations with opposite binding, and so that's that. So this is very consistent with the idea that you have a pair density wave creating a charge density wave. If you didn't have a pair density wave, then this whole mechanism would fall apart, and there's no way, there's no simple way of getting these dislocations. Yes? Go ahead. Oh, should you?
Other than
Correct, absolutely, but with magnetic fields. Yes, yes, haven't done it yet. Go ahead.
So if KDW is the largest state from superconductor, uniform superconductor, CDW is the largest state from uniform and KDW. So KDW should go to 0 at the uniform vortices and the KDW. That's what you see in the but the KDW vortices.
We can't see the vortices in this compound clearly, but we have there's a we can take all these dislocations, put them on top. This is just for one of the 3 solutions. We can add all of them together and ask if there's some bunching, and actually there's some bunching, and the number of bunches corresponds approximately with the number of vortices you expect. But I have to say our field of view is not big enough to do anything statistically significant. Let me, Ashwin.
You don't see the vortices themselves.
No, we don't. And one of the reasons we could, it's a difficult experiment. One of the reasons is the density of states is so high at the Fermi energy. And the way we usually see vortices is through the bound states. So that there's a contrast. There's a bound state inside the gap, and there's a contrast. Here, it's just really hard to see vortices because of the, this gigantic density of states. And so the contrast would be tiny. Also, to see vortices, we would need to scan in very large areas. And it's really hard enough to see the superconducting gap with this, the gap that we see. If your tip picks up one impurity, then now you can't see the gap anymore. And you have to it's very delicate. You have to be careful.
What these dislocations are associated with this?
They would be, in theory, but we can't see the vortices directly.
Does the density of dislocations make sense?
That's what he was asking, and I let me actually, I have a slide for that. Let me actually show you. This is the CDW melting the temperature, and it goes away at around 4.6, 4.7 Kelvin. Let me just show the density of dislocations. Oops, let me actually, I have it here. Be up here. If I can't find it, then I will. I will. I can't find it, but let me just say that in this field of view, if you put all the dislocations from all three directions, this is just one direction. So on top of each other, you get, like, for example, at 8 Tesla, you would get sort of 3 bunches. And those 3 bunches, that's how many vortices you expect in this field. This is 0, 0 to 10, so this is probably 8, this is probably 5. This length scale, length scale is, this is probably 400 angstroms, so 40
You, perhaps to see similar field dependence if the CW wasn't the daughter of the pair density wave, but coupled to spin density wave.
If you have,
Because there was also this funny feature in the susceptibilities, right?
Yeah.
Um,
so, but nobody's found a spin density wave. That doesn't mean it doesn't
if
exist.
the CW is so weak, then SW could also be extremely locked to.
It's possible, although I don't understand why it would be sensitive to HC2 though. Because we have data in 2 different directions and it goes like HC2. And so. So that's a good point. And so none of this phenomenology as such would be, it would explain this, but then it wouldn't explain the HC2 effects. Yes.
So is the CW
Yeah, we are in final discussion.
Final discussion.
Yeah.
I've got
11:20.
I've got 40 seconds.
Yeah.
Okay. It may be just on the surface, we don't know.
If it is a PW resisting the CW with uniform, then these dislocations should actually be half.
They are halfway. They should be halfway.
So you see the.
We can't see, I mean, we have to really do this. We have to turn on a field, find the vortices, look inside the vortices. A large field view. We haven't been able to do that. It's a hard experiment on these guys. As a done.
All right. Technically, we're over, but we're gonna have. Can you rule out intertwined?
Intertwined is what I thought the Ginsburg-Landau was, but did you need something about more than that?
So I'm not a theorist, but I think just had different order parameters that were put together in some Ginsburg-Landau expansion, and that's, as I understand it, that's different from intertwined order, where you go to some state with higher symmetry. And so maybe, the concepts of independent vortex or dislocation then disappears because you've got some defect in some intertwined state.
So I don't know.
I think that's what they were.
I thought the Ginsburg-Landau was that, but because here in the Ginsburg-Landau, the way it would work is, maybe this answers your question. If you turn on a magnetic field, any vortex of the homogeneous superconductor would be net associated with these half vortices of the PDW, which would then create dislocations in the charge. So.
Then they what we see gets charged against the gets we get independent.
So I will just tell you what I've been asking this question, and the answer I'm getting from Julian and Eduardo is
It's not serious.
it's possible, yeah,
Why should we see evidence against people
about
an observation? Even above and below.
below. I don't see any direct evidence for PDW myself. Shuchi sees something, but that might be consistent. But they can't say it's parent or daughter. It could be either way in their case, right? Like if you have a CDW at high temperatures, which has nothing to do with the PDW, you cool down below TC, you get a PDW as a result. So the question is, which is chicken and egg is the problem?
No, do you see evidence of their density wave anywhere in SDN on the samples?
How-
Maybe there's some machines
We haven't checked with the superconducting yet. And their samples and our samples are identical. We have the same samples. We haven't checked with the superconducting tip.
We have superconducting from this.
We can check, but they've already done the experiment. So,
Seems to be like this is, all of this building up is very exciting. But beginning, we have to show evidence to.
but I don't know what you would want as a signature, because do you accept Seamus's as a signature is the question.
Part of the problem is there's no phase sensitive STM at the moment.
No, but here they have.
No, if you have a super, all you see is a pair, you have a density wave of pairs. How do you know that
You're gonna,
that is E?
Well, you just said we got a field.
no, they don't have phase information. No STM is phase information yet. Amplitude.
We have some phase, but the question is not the superconducting order, unless you have areas where the superconducting order has a phase shift. In that case, you'll see something on the boundary. Then you have to. Yeah, if you have two different areas of PDW with a phase shift, then at the boundary, you'll see something, which might be interesting.
And another thing, maybe I can figure out just the way is commensurate.
Incommensurate.
Another.
It's in one direction, it's half the Taylor interval. So it's twice. Two lambda is twice.
Before we go on, do we have a group agreement that we're gonna push the schedule by 10 minutes?
Yeah.
Because otherwise, we can't go. Okay, we can have more questions. Okay, good. Yeah.
I asked what I like to ask you. So you said this is inclination. Then the question is, if you have inclination doubly, then you have a lot of strong folding, and the film itself is going to extremely complicate. Therefore, there's a lot of interdependent
Correct.
which will kill the superconductivity.
Right. So let me just say that, this is a very weak CW. It's the total density of states is not very large. When we can't even see it in the topography with your naked eye. Usually, Uraniumbased and I, you see the CW with your eye. The only way we see the CW is through the Fourier transform. So I'm not sure that this is going to cause, so, we've noticed in other materials, depending upon how strong the modulation is, your folding is not that strong. So if it's a weak CW, it might not have a huge effect on the band structure. So that's just one glib answer. The actual answer is, I actually don't know what the Fermi surface is. That's the problem with these materials. We have like 2, 3 pieces of information. We have some Haasman alpha measurements that show oscillations. We have 1 or 2 RFS studies, and that's it. We need more data.
Another state question is, in the course of this CW, is coming from the P band or within E band or both?
Cannot tell, how would we know?
Well, I think it's something too low, but if you do X-phase tapping.
Temperature is too low.
Yeah, something too low, but if you can distinguish those things.
Yeah, 4.8 Kelvin is hard. 4.8 Kelvin.
But actually, I mean, it's actually asked that question.
Yes.
The CW that's messing up the P band or G band.
The D and P are mixed, by the way, on the Fermi surface.
Questions from the back. I did see some hands up earlier, but no. Before I go to the front. Yes, okay. Please.
That's a really good question. I don't know that we've been trying to answer that question. One thing we try to do is to see if perhaps if you look at the PDW directly with a normal tip, and can we see the oscillations in the superconducting gap and what's the size? Sometimes we think we can see oscillations that are much bigger, like on the scale of like 50 or 100 microvolts. If you take a line cut along the atoms, you see oscillations on the, you can see these oscillations twice the atomic distance with a pretty large amplitude. So I'm not sure. So one possible answer might be maybe the PDW, energy scale is bigger than that 10 microvolts, maybe that's why. Another possibility, I actually don't know. You know, if the PDW is weak, you'll still get a CDW. You'll still get a CDW. It's just, what Q you see it best. It will affect which Q you see it best at. When you see the Q better or 2Q better, that's what it is.
Okay, more questions. Well, Frank is next.
So, yeah, I think yesterday it looked quite convincing that the CDWs there, temperatures higher than potential PDWs. But in order to answer the question, couldn't you, what is parent and what is daughter, couldn't you just repeat this experiment at different temperatures and see if at a certain temperature you no longer induce dislocation pairs in the CDW?
Yeah, so we have to do that.
So this is at
This is at low temperatures. So all this is at below TC. So we're trying to do that. We're trying to do magnetic field dependence at higher temperatures.
Ash.
So it's probably the most surprising in this material is high field. We enter the superconductor.
Yes.
So are there any prospects for doing STM on those fields, or it's just out of reach?
So along the B-axis,
The fields themselves were.
the field is like 20, between 15 and 20 Tesla. 15 Tesla is reachable. But you want to actually get the low TC stuff. Because all the energy scales go up in the high TC systems. So you want to do this in the low TC samples. The real problem is the cleave is in a strange angle. And we're at an angle of 24 degrees between B and C. So there's two problems. At 24 degrees, I think you're not in that little area where you see for the first reinforcement.
Time for what? No. We can't do it. Alina is the last question. Here we go.
Didn't appear in this context. My question is how do experiments and the rate and rate compare with this? Are they the same?
No, they're not the same because there, if you turn on a magnetic field, you close it with an affinity, and you see the fairness inside the vortex core.
You mean the charge density wave inside?
Yes, but I think Seamus has done. Has Seamus done?
Yeah, I think so. Now it's charge density in the core is a pair density.
But you don't see the pair density wave above HC2, right? I don't think so.
No. That's but you see the pair. You see a pair density wave in the vortex, right? He's done measurements with superconducting. So there, at least inside the vortex core, you do see, at least I think I remember superconducting measurements inside the, maybe I'm wrong, inside the vortex core, and you see the pair density.
Sure, within the superconductor.
Within the superconductor, but inside a vortex core.
Yeah, maybe. I'm not sure.
I think the phenomenology is different, actually. In Visco, I have not heard of the PDW. Of the CD, no, there's not a CDW I know of that disappears in any system. I don't know of any such CDW.
Okay, let's thank Vidya for a great talk.